Hello, my name is Dr. Bradley Alicea, and together with Morgan Huff, I'm presenting the augmentation of intelligent agents for human-machine superperformance. We're both affiliated with the Orthogonal Research and Education Lab. So when we talk about human-machine superperformance, we're really talking about these symbiotic systems that involve a combination of human intelligence and machine intelligence. So when humans and machines work together, they can leverage complementary strengths. And again, this is something called human-machine symbiosis. So if we go back to 1957, Herbert Simon made the prediction that in 10 years, a computer will be able to beat a grandmaster chess player. Well, it took a little bit longer than 10 years, but in 1996 that finally happened, and Garry Kasparov was defeated by Deep Blue. So what happened after that was the development of something called centaur chess, where supercomputers and humans leveraged their relative strengths to build a better chess game. So in this paper we reference something called a world model. This is an evolving area, so these points are very general. A world model should provide a conceptual framework, a representation that helps a computational model interpret incoming instances from the environment. The second is that a world model should build a compact state-space representation based on sensory inputs. A world model should predict the consequences of potential actions. A world model takes a high-dimensional and stochastic sensory signal and reduces it to a compact representation. And then point 5 is that world models are a model of all plausible simulation scenarios. Basically, the first 2 or 3 points are what typical neural networks or deep learning models do. And then 4 or 5 add additional models, such as reinforcement learning or a symbolic model. So the first example I'll show here is this paper, World Models by Han Schmidt-Huber, and this was published back in 2018. The machine tries to not only take the inputs and produce outputs, but it takes inputs, it builds a world model or a model of all possible states of the simulation and operates from that. So in this instance, it's trying to drive a car around a racetrack, and to do this, it builds a compact planning representation. Sensory sampling is a predictive model from a probability distributions. What you find in this example is that planning and sampling are balanced, and that balance comes through a generative. We need to do some planning, but also some sampling from the environment to make sure that it's on the right track. Now, we talked about planning and sampling in our paper from 2023. We can also define super planners and super samplers. Those are those individuals that have a high degree of planning or high degree of sampling. In this relativistic regime, you get high planning and high sampling, and that's what we'll be talking about with respect to our human-machine superperformance. This is where we have a pursuit evasion model, and we're looking at the coevolution of agents where one has a high degree of planning, one has a high degree of sampling. The paper is called World Models in Artificial Intelligence, Sensing, Learning, and Reasoning Like a Child. They propose a world model where you have humans in the loop that update the model. You have physics-informed modeling, which is also embodied. You use a neurosymbolic component, you use causal inference, and you have this open-ended machine learning model. So you have a training set, and that training set is interpreted by the world model, and that provides a higher level of awareness or intelligence. Another thing that we talk about in our paper is this idea of the flatland problem. There's a book from the 19th century called Flatland, A Romance in Many Dimensions by Edward Abbott. He provides this thought experiment, creatures that live in a one-dimensional or two-dimensional world, and they're interacting with a three-dimensional world. So the idea is that those creatures can't conceive of a third dimension, and that third dimension disappears. It's relative to the viewpoint of the agent. The flatland problem is a problem of low dimensionality. There's a lack of dimensionality, and it impedes the ability of that model, or that internal model in this case, to understand the full picture. And so this leads us to this idea, the world always having a higher dimensionality than the model. So the model usually doesn't have as high a dimensionality as the world. And indeed, in machine learning models, we usually do a lot of dimensionality reduction. Machines often don't capture the full dimensionality of the real world through their inputs. So in the paper, we introduce a number of variables. The first is that of the sensorium, which is this from a paper we've done on something called Gibsonian information. And this is describing the dynamic experience with an agent sensory world. So an agent interacts with its sensory world and it extracts these parameters, which are then calculated into the sensorium parameter. So we have what we call coherent movement. So in the environment, there's usually some sort of coherent movement against a background or amongst particles or something like that. And then we have information decay, so that coherent movement decays, maybe masked by noise. Then there's an internal experience of coherent movement. So internally, the agent interprets the coherent movement through their sensory apparatus, and it's represented or it's sort of processed in a way that's different than the coherent movement. And so that's divided. We take the internal experience of coherent movement from the coherent movement, and then we subtract sensory delay, which are the delays in getting information, which serves sort of as another aspect of decay or another dimension of decay. We also have this issue of the ecological psychology of the sensorium. So the sensorium is important because in the world we have all these things that are moving around us constantly. And as an agent, you have a world model that represents these points. It represents the motion of these points, and then it represents these different parameters of the relation between the intelligent agent and objects in the world. And so this shows kind of that relationship. Then we have these sensory modality specific gradients. So we have the sensorium, but then we have these gradients through each sense. And so an agent can have multiple senses, and multiple senses, in fact, are needed to build a world model, to build an intelligent system. Each sensory modality, source of input, forms an input vector. The input vector is represented, the nabla describes the gradient, which is sort of the direction of change. So you go from these vectors to these gradients, and then you go to an angular displacement between those vectors. So you look at the difference in how these gradients are being explored by each sensory modality. And so this is kind of an example of the exploration of this gradient. It's a two-dimensional gradient, and then there's this path that goes down the gradient. So we define intelligence as a function of multisensory and 4D spatial worlds. So we have 3 dimensions of space, 1 dimension of time, and this is the representation here, which is I, and I stands for intelligence, and in this case it's the difference between generativity and selectivity. A couple of notes here. Low degrees of generativity are penalized relative to both low and high degrees of selectivity, and superperformance, as we've defined it, maximizes both generativity and selectivity. In those cases, intelligence is amplified. So we have generativity and selectivity. So generativity opens up the number of possibilities, whereas selectivity selects the most optimal, interesting possibilities. And so you need both of them maximized to really get a high level of intelligence. And so we have a couple of cases where we play around with different values for both G and S, and we end up with different values for intelligence. And we find that generativity is important, but so is selection or selectivity. So here is our figure for both the intelligent agent and the world model correspondence. The interesting thing to note here is that each of these intelligent agent and world model have a set of discrete states. This operates according to a state-space model. So the state-space model has to correspond. So in other words, the same or similar number of states in both the intelligent agent and the world model are considered well-regulated or well-controlled. Whereas if there are more states or many more states in either one, then it's poorly controlled or poorly regulated. And so this is an example. If we use Shannon information, we can see that in this case, a world model has a much higher level of Shannon information than the intelligent agent. And so we ask the question, how well does the state space in A match the state space in B? And so if A and B are ill-matching, there's this anti-aliasing process that goes on. And so, we might ask, in that case, if we go from one state in A, we can map to multiple states in B. And so it's hard to know which state to map to. We also can't really determine how feedback should occur. So if we get feedback from one of the smaller, more specific states in B, that maps to the more general state in A, but it's hard to know what for A to interpret that feedback. And then, of course, if we have closed loop positive feedback, if we have more and more states in A, then it's easier to map or correspond to the actual phenomena in B and vice versa. And so this leads us to some interesting questions in intelligence augmentation and distinguishing that from artificial intelligence. So instead of using data and algorithms to simulate human intelligence, intelligence augmentation uses data and algorithms to work with or complement human intelligence. So this is the natural intelligence amplifier as defined by Ashby. You have a regulator X and a system S. You have an intelligence measure G, which is what the regulator is sending to the system to act upon the system. And then there's this corrective signal or feedback in U that improves the performance of the regulator. So if the regulator is maybe it's like a person operating in the world, being able to do things in the world competently, walk through a building, navigate through a building, read a map, things like that. And then if they make a mistake, there's a corrective signal or feedback to help them improve their performance. Now what we're proposing here is a super performance enhanced intelligence augmentation. Using a similar model as we have to Ashby, except that we have a couple of differences in both the feed forward and feedback components and the agents. So here we have an intelligent agent acting upon the world with intelligence, but the part of the world they're acting on with the intelligence is the generativity component of our intelligence definition. So we get a higher level of generativity. It can act upon the world model in different ways. It can act upon the world model more specifically. And then there's a selection action. So if there are a lot of different options that it can act upon the world model with, selection then restricts the states of the world model and makes the whole thing more specific. And you can see the part of the equation that's relevant here. So this actually can be shown in the real world in video game performance, where you can improve someone's expertise by making them play a video game for hours and hours and hours. And it's interesting to note that in real world performance, it isn't linear, and it isn't even log linear. It has these dips and nonlinearities in it that maybe are described by our super performance model. And so we can even extend that further to open looped intelligence augmentation, where feedback from the selective component is more sporadic. And this may actually help shape the world model states even more. So it can open up the loop for adaptation to new situations. So how do we construct good world models and achieve strong intelligence augmentation? And so one of those is appealing to the idea of variety from the Evergood regulator theorem. And in the Evergood regulator theorem, it says that variety can destroy variety. And this is the case where too many states in a world model without a corresponding representation of the intelligent system acts to destroy information. So these anti-aliasing mechanisms actually destroy information provided by the source of the intelligence. And so we can solve this by modifying the amount of expressivity of our generative process of intelligence. So it means that we want to be able to create a number of alternatives or a number of alternate states. And so that process, we can tweak that. And we want to tweak it to match the intelligence's learning rate. So we want to match the performance of both the intelligence and the world model so that it can successfully learn and represent all necessary state information. And finally, the high quality of regulation provides a means for strong AI. So finally, when we have a high quality of regulation, it provides a means for strong intelligence augmentation. So what is the quality of regulation? What is the quality of this regulation between the intelligence and the world model? Is it good enough to enable this sort of augmentation through feedback or through open-ended means? We want to enable the conditions for maintaining information acquisition via feedback. And so there's this example in the paper of a human learner using a dictionary. The human learner is the intelligence, and the dictionary is the world model. The human learner often does not know all the linguistic states or words available in the dictionary. If the learner acquires too few words, the dictionary is not a suitable intelligence augmentation tool, and instead requires a more detailed curriculum for an instruction, and this is where we get this augmentation process. The dictionary that is missing too many linguistic states will hamper the learner's ability to augment their intelligence, and a learner using a dictionary as a lookup function supports the well-regulated acquisition of a larger vocabulary. Thanks for your attention.